talk today is going to be about design to test workflows with an emphasis on data and IT management in the chiplet ecosystem. You heard I work at Keysight Technologies, and we recently celebrated our 10-year anniversary at Keysight. We actually have a long history, more than 85 years of history. And show of hands, does anybody know that history? Do we know where Keysight's legacy comes from? A few hands up. I like to call ourselves the oldest 10-year-old company in Silicon Valley. And here's a clue. Here's a clue of where we started. And if you don't recognize, many people call this the birthplace of Silicon Valley. It's a small garage in Palo Alto where Bill and Dave built HP. And Keysight traces its legacy all the way back 86 years ago to HP. We have businesses that were started at HP that got spun off at the time in Agilent Technologies. We were Agilent for about 14 years, and for the last 10 years, we are Keysight Technologies. One of the other interesting things about Keysight is it also has an EDA business, and we've been in EDA business for more than 40 years. And I'm not sure if everybody realizes that it's a very thriving business. For the purposes of conversation today, Keysight solutions, both hardware and software, that play in high-speed digital design is what I will cover. But Keysight covers many solutions in many other areas outside of this, outside of high-speed digital. And my quick introduction, I've been in EDA for 25 years, and I've been in various different roles, and I like to say most of my roles are connected through partnerships and collaborations. So when I look at this room full of people, I look at a lot of potential partners that I can work with in the future. So I look forward to that conversation. So I have three main topics for today. One is how do we do better designs for chiplet interoperability. The second one is how do we do better testing for chiplet interoperability. Third is around how do we do data and IT management in the chiplet ecosystem. Before I go into that space, I want to take a look back almost 50 years ago to another industry that has lots of parallels to the chiplet industry today. And this is the computer industry. In those days, we still had mainframes, and we were just moving away from mainframes into mini computers and microcomputers. And at that time, the industry was a monolith. If you bought one of these computers, it all came from one company. Every single thing was designed by that same company. Peripherals, CPUs, monitors, software, operating system, everything pretty much came from one company. And we know how that went, right? We know the change that happened, and with the advent of the modern IBM PC, the industry went from being a monolith, a vertical, to horizontal. We saw a lot of specialization. Companies started designing things and just one thing. Like you would have companies just design keyboards. And as long as you agree on and standardize on a connector and the number of pins in the connector, your keyboard would work with any computer. So standardization showed up. Standardization showed up inside the computer, on the motherboard. Buses like PCI Express was a standard that came up, allowed you to mix and match different chips on the bus. As long as you agreed on the data standards and you agreed on the pin configurations and various different things, you could mix and match, and you could actually have an ecosystem where specialization worked. And all of the advantage of this multi-vendor ecosystem was we could scale. A couple of days ago, Paul mentioned the Cambrian explosion in one of the panels. And that's exactly what was happening in the computer industry at the time. There was a Cambrian explosion, and there was so much need for extra computing that a monolith industry couldn't serve it. And going into specialization, going into standardization is the way the computer industry solved this problem. This is sort of happening in the SoC space with chiplets, right? We can have SoCs that are done all within the same technical node. Everything is designed from one foundry, but we are shifting more and more towards a design with multiple chiplets, with maybe different nodes and a lot of fast interconnects between them. So that's the packaging piece of it. And allows us to think about what makes sense to scale to the next node and what makes sense to leave as is. And this allows you to manage for risk. This allows you to manage for engineering time and turnaround time. Not everything has to scale, not everything has to change to the latest node. And so that flexibility allows you a truly multi-vendor, multi-process ecosystem where if you were building an SoC, you could have your own secret sauce, your own special process. You could mix and match and buy chiplet technologies from various different vendors if you needed to, and you could develop an entire ecosystem here. Of course, this is the vision. Not everything is solved, right? There's a lot of challenges, and this group of people in the Chiplet Summit encourages us to come together and solve those challenges. I have another take on chiplets, another flavor on chiplets. Many years ago, I met Professor Swaminathan. At the time, he was at Georgia Tech, and we were at an IEEE conference, and he presented on packaging, advanced packaging techniques. And to my memory, he was the first person who mentioned that Moore's law is not keeping up, at least as far as just pure silicon is concerned. But if we reframe Moore's law as a system problem, as a packaging problem, there is still an opportunity for Moore's law to come up. The phrase chiplet didn't exist at the time. Sys-Moore, I don't think existed at the time, but essentially that was the topic being held. More recently, met Swaminathan again. He did a presentation at Keysight, and this is one of the kind of slides out of his paper. And this allows us to envision chiplets in a different way. To me, chiplets is not just about digital. It could also be RF or analog or mixed signal. Chiplets is not just silicon. It could be exotic materials, compound semiconductors like gallium arsenide. Chiplets is not just about AI data center compute functions. It could also be used for aerospace defense applications. Chiplets is not just electrical, it could also have optical photonics ICs in there. So there's a lot of different ways that chiplets can enter our world, and there's a lot of opportunities here. Some of you may know Keysight has its own foundry, Keysight builds its own chips, Keysight builds complex instrumentation, and this flavor of chiplets is something that we really like. We are also exploring how our future products utilize chiplets for our solutions. So with that kind of background, let's go back to the main topics. So simulating for interoperability, this is a very good story about partnerships and about how we started looking at the UCIe standard. We're working with AlphaWave actually on PCI Express. And after attending one of the Chiplet conferences, Chiplet Summit sessions, we talked to AlphaWave and discussed the new UCIe standard that was being proposed. And we found a very good partner. AlphaWave told us a bunch of requirements that they had, what they were looking for, what their customers were asking them to do. And we worked together to come up with a plan to approach this. In the PHY layer, what you're really trying to do is trying to understand the signal integrity performance from one chiplet die to another. And while you do this, you need to have a lot of variability that you need to analyze. What if I was using a standard package? What if I was using an advanced package? What if some of the configurations changed? So you needed to get different models representing the chiplet die. You also had to worry about the interconnect between those two chiplet die. It could be as small as 1 or 2 millimeters. It could be as large as maybe 20 millimeters. And the signal is traveling through interposers and packaging and through silicon vias and getting to the other chiplet. And so how do you have a pre-layout model for that or a post-layout model for that? And while you're trying to figure all of this out, another innovation that had to be done was how to manage the forwarded clock along with the data. And UCIe recommends that clock could be quarter data rate or half data rate, and we had to figure out how to simulate that for performance. and we were able to get all of this done. Today you can run simulations where you can get a full UCIe compliance report with chiplet to chiplet communications. We also had to work on another KPI for UCIe, that's the VTF, or voltage transfer function, that gives you a good clue on crosstalk performance. Crosstalk has a signature. You can see what near-end crosstalk or far-end crosstalk means, and you can see some of the signatures in the eye diagram plots on this, but it gets simplified into a simple crosstalk limit voltage transfer function. So that was another KPI that was added in the simulation options. In December last year, they had a press release. They have UCIe IP for sale. They also have other interesting chiplet IP, and so this was a great partnership project around how do we do better designs for chiplet interoperability. All right, let's take a slight shift to our second topic, which is how do we do better testing. And if you look at other standards, maybe PCI Express or USB, there are different ways to do testing. One popular way is to do plug fests. You show up at a big conference room or a ballroom at a hotel, and a bunch of different vendors show up, and they all bring their devices. And then you plug them and see if they talk to each other, and see if it works out of the box, and if it works, great. And if it works, does it meet all the compliance specifications, all the different hundreds of specifications? And if it does, great. And if not, you debug. And I've been to some of these plug fests, and Keysight participates with a bunch of instruments and measurement equipment. It's very, very loud. All the fans are whirring away with all the different network analyzers and scopes and stuff. It's very loud, and this is a traditional way of doing things. I don't think we are going to be able to take this to chiplets. It's not conducive in the environment. So here are a couple of strategies on how you can do testing in the chiplet environment. So let's take a look at the passive structures. Everything after the signal exits out of the chiplet, all the passive structures, all your through-silicon vias, the packaging, the small bits of transmission lines, you could use microprobes and measure it using a network analyzer, outcomes and S-parameter file, and you could use that for your testing. As soon as you come to the active structures, the actual chiplets, we are talking about the transmitter and the receiver. The transmitter could be measured with a high-end oscilloscope, and you may have to de-embed certain parts because you may not be able to probe exactly where you want to, but using an oscilloscope, you can come up with a transmitter test. And when it comes to receivers, you can have a gold standard signal being generated by a BERT tester, a bit array tester, and you can inject that into your chiplet and see what you get out of the measurement on chip. So one of the things that you will see is the concept of BIST, or built-in self-test. So a lot of the chiplets come with its own on-chip measurement technologies, and an independent and accurate measurement companion like Keysight can help you improve your BIST. So BIST may be overly optimistic or may not account for all the non-linearities that may be happening at the measurement scale. And so you can calibrate what's happening on the BIST test with a real test coming from an oscilloscope. And sometimes the BIST doesn't decompose the signal. The signal that you may get from the on-chip measurement has what happened to the transmitter, what happened to the channel, what happened to the receiver. And if you have a problem that you're trying to debug, you need to decompose at which stage does the eye look different. And so an independent measurement from a scope can help you figure that out. So here are some strategies around how we can perform testing. Let me switch gears to another topic, which is what about data management and IP management? There's going to be a lot of data in a chiplet ecosystem. You may have things coming in for memory, you may have I/O, you may have storage. There's just a lot of different things, and this is just for one problem or one customer. As you change the nodes, you may have variants of this. As you change your customers or your suppliers, you may have many variants, and as you start looking at this problem, it becomes very complicated. Trying to keep track of what is going on using just pen and paper or using spreadsheets is not going to be very easy. You may have to keep track of what was the last known good die that you sent to a certain customer. You may have to keep track of who has access to all of the data for this known good die. You may have to keep track of what security you put on there because you're working on a restricted project or you're working on an export regulated project. You may have to supply a bill of materials at the end of a project to archive your data. A lot of these things are complicated, and what you probably need is an enterprise level engineering lifecycle management tool. So Keysight has some solutions in this space, and there are ways to use this to manage all the different chiplet data that you may have, and the IP that you may have, and that you need to work in a bigger ecosystem. So lots of opportunities for data management. At this point, we are coming close to our bonus topic, and as happens in a typical semiconductor conference, we all use the same terms. So I think I've covered a lot of these terms already. If you're playing keynote bingo, the one topic that I haven't covered so far is AI and AI/ML. And I know Boyd covered this also. So everyone does the game of what would ChatGPT do? So I tried to do the same thing. What would ChatGPT predict about EDA and chiplets in the future? It gave me 5 pages long of data, and I said, scrunch it down to 1 page, and gave me back 1 page of data, and that's what it said. It was pretty impressive and a little bit scary. And I decided I'm not going to give up my job to ChatGPT yet, so I'm going to ignore everything it's shared, and I will do my own predictions. So here's, based on my history and my experience in EDA and how AI is going to impact EDA. So the first area I see is just automation. One of the opportunities we have, and we say, is machine learning. And by definition, for machines to learn, machines need to operate a lot of what humans used to operate. So if you were doing workflows and you were doing design and you were using the mouse to run a piece of software, it needs to now run with APIs. As long as an API can control that piece of software, then there's an opportunity for machines to control that software. Even if you don't do machine learning at the end of that, the fact that you can operate it using APIs and scripts allows you to do a lot of automation. So I think automation is just going to go through the roof as we look at the later part of this year and in the future. Another area is all around agents. This is ChatGPT like chatbots and co-pilots and being able to talk to a piece of software. But most likely, your chiplets may come with an agent. And you may be able to query that chiplet on what was the last known good configuration for it, which SOCs does it thrive in, which SOCs it may not work out. And rather than try and read a data sheet or talk to a smart application engineer, you may be able to actually have conversations with agents that come with chiplets and maybe many other tools and design tools that you may be using. Another area is around surrogate modeling. I talked a little bit about passive structures and modeling that with a VNA and getting S-parameter data out. You could also simulate those structures in a 3D EM tool and get S-parameter data out. And so my customers today have thousands and thousands of S-parameter data, and they struggle managing that level of complexity. And this is just for the passive structures. But we have a way to convert them into surrogate models. We can use artificial neural network modeling techniques and convert thousands and thousands of S-parameter data and collapse it down to one ANN model, much smaller in size. And you could apply this technique for a lot of the different chiplet problems. So I think surrogate models have a big role to play in our near future. And finally, the holy grail is our version of AGI is synthesis, right? if I've done 100 designs in the past, if I'm doing wireless transceiver design, I've done 100 antenna designs in the past, why can you not do my next one? Just look at all the work that I've already done. Here's the frequency range that I want to have this MIMO antenna structure be built, and just build that for me. So there are very many different places where we can apply synthesis, and I think this is also going to be one big area of opportunity for us.